Hi, today we are doing lab number 4 and let's get started. First of all, we need some different functions to help us during our homework. So, we had a function that converts degrees into radians, function to create a rotation matrix from Euler angles, a function to create a rotation matrix from a quaternion, and a function that helps us read external files. So, now that everything is settled down, we can start. In exercise 1, we need to search the origin of A seen from B, the origin of B seen from A, and the coordinates of Q in A. And that's what we are doing in that exercise. So, first of all, the rotation between frames, if the XA makes a 30 degrees with YB, then the whole degrees is 120 degrees. So, the rotation matrix is that. So now that we have that rotation matrix, we have to find the origin of B seen from A using that formula and rearranging it in that way, and then the origin of A seen from B, and finally transforming the point Q with that formula. And if you see here, it does what we are looking for. In exercise 2, we are given different origin points, rotation A, rotation C, and 2 points defined in frame C. So let's get started. First, our rotations. The rotation matrix corresponds to rotate around X, then around Y, and then around Z. And our quaternion rotation has a unique quaternion that defines our rotation matrix. So now we have this. Our affine transformations from C to B is defined with this expression. Then from C to A, that's a composition. We substitute B into A. We have this, and it gets that. Now, our segment visualization. Our segment endpoints are transformed into frame B and into frame A. And to see that, first, that's our code. This is only to print on the screen what we are doing. And let's see if it does. And as you can see here, our frame transformation to C to B, from C to A, our segment in frame A, and our segment in frame B. And then our segment in frame C. Now exercise 3, our camera projection. Our problem says that points lie on a circling world frame W. Our camera is set at a specific point. We have our orientation about Y and about Z, and we have our focal length. So, first of all, we can define our camera rotation with that. This rotates world axis into camera axis. Then, our world to camera transformation. To express our point in the camera frame, we have that expression that it became that. So this moves the world so that the camera becomes the origin. And finally, we have our perspective projection. Once a point is in camera coordinates, we have this function. This is the pinhole camera model. This is exactly what the code computes. So let's see if it does it correctly. And as you can see here, loaded 63 points from A1. So we have it in here. It does it correctly. Finally, exercise 4. We have two segments defined by 4 points. We have to compute the minimum angle between segments in 3D and the angle between segments in image plane. And the camera defined by axis angle, rotation, and position. So let's begin. We have our 2 segments, our angle formula and the minimum angle. So for the camera rotation, we apply the Rodriguez formula. We have the unit axis and an angle, so we apply the Rodriguez formula that we know. Then, to transform the to camera coordinates, we apply that formula, and finally, after the transformation, we keep only the x and y components and compute angle using the same dot product formula in 2D. This simulates what the camera sees after a projection. So let's see. So segment 1, our segment 2, and then our different segments from camera, world and camera. So this is my code. This is how it prints, and how I manage the structure. That's very simple.